Making decisions comes with consequences. Ideally, consequences that we like. If we could predict the outcomes of our decisions with 100% certainty, the world would be so much simpler. We would always know what to expect. Those predictions of our future are more common in our everyday lives than we might realize. Many of us don't even leave the house without relying on them. They are mathematical models using linear predictor functions that use data to estimate the unknown model parameters. A very popular method is called linear regression. The basic idea is to map the effect of an independent explanatory variable onto a dependent response variable. Such models can help us to describe the underlying relationships and predict situations that we have not observed before, or help us to eliminate errors from our data. Whenever I saw linear regression in the past, I noted it as something simple enough that I don't have to dive into the details too much. But as so often in life, when you find yourself in a situation where you actually have to use it, a lot of question marks appear. The general idea is simple. You're looking for a linear function that fits a set of data points as good as possible. As good as possible meaning minimizing the squared distance of each point to the function, for example. But we'll get to that in a second. When I looked at the general formulation for the first time, I got really confused about the double index for the data points. This is when I learned about the difference between multiple linear regression and multivariate linear regression. The multi implies that we're not only looking at one variable influencing the outcome, but possibly a few of them. While multiple linear regression predicts a single scalar value, multivariate linear regression predicts a vector, containing multiple variables that are correlated with each other. So the double index simply comes from taking multiple explanatory variables into account. In the simplest case, our model just ends up being a linear equation with two parameters, the y-axis intercept and the slope, as well as one independent variable. Looking at one specific data point, we can describe it as the way to that data point, plus a little extra term epsilon. The small epsilon at the end of the model is the noise. It's basically an error term. Sometimes people like to call it noise because it acts like noise if you regard the actual model as the signal. Having errors and the need for a regression line in the first place implies that there are unknown factors. Otherwise, our data points would already create a perfect line by itself. Let's look at our basic equation for each data point again. We can rearrange it to describe the error explicitly. Our best fitting line will have the smallest noise possible. But what does that mean practically to compute our regression line? It means that all our errors summed up are the smallest possible in case we choose our optimal regression coefficients. To escalate the impact of bigger errors, this term is squared in the least squares method. It simply means that a bigger error will have a higher impact on the correction towards them than smaller ones. Finding those optimized model parameters means we have to find a combination of them that gives us the minimum of our newly defined function q. To actually find those optimal model parameters, we have to take advantage of basic calculus and find the minimum by deriving with respect to those coefficients and setting those equations to 0. Doing so gives us a formula that we can apply with nothing but our data points. All these terms can be computed having the data points themselves and the overall amount of them. We're technically calculating statistical properties of our data here, like the sample mean and the deviation of each point. Such correlations do not necessarily mean that any of the explanatory variables are actually the cause of the effect that we're observing, but there are methods to figure that part out that we'll discuss more in the future. Even though many situations cannot simply be modeled as a linear function, in most cases it still gives us the necessary information to make an informed enough decision. They help us to quantify effects and make the best of what we already have. It is still up to us as humans to put that information into context and take responsibility for the choices we make. But like a beacon on a foggy day, these tools guide us through the chaotic sea of data, recognizing patterns, revealing insights, and empowering us to make sense of the world, one prediction at a time.